Hi everyone, here we are in week 4 of pandemic learning. We're going to be solving exponential equations and also looking at some applications for them. What's unique about exponential equations compared to every other kind of equation you have solved in the past is that the variable, our unknown, is in the exponent position. And I said here our goal is going to be to use algebra or exponent laws to get to the point where you have only one power term with the same base on each side of the equal sign. Once you get the solution to that point, then the exponents will be equal and you can solve for the value of the variable. In the first example, I have a power term on the left, 3 to the power of x, and I have the number 81 on the right-hand side. Remember, our goal is to get one single power term with the same base on each side of the equal sign. And the number 81 conveniently can be changed to 3 to the power of 4. And now that I have the same base number and a single power term on each side of the equal sign, I know that the exponents are equal to one another. So I write, therefore, x equals 4. You can quickly check to see that the left side equals the right side in the original equation for any of these questions. That's the beauty of questions that have the direction solve. You can always check to see, did I actually get the right value? Because your left side will always equal the same as the right side. So 3 to the power of 4 definitely is equivalent to 81, so we can just do a quick mental check there. In question B, I have a single power term on each side of the equal sign. They already have the same base. That means the exponents are equal to one another. As soon as you shift to working with just the exponents, put your therefore symbol down, and then set those exponents equal to one another. I have set this equation equal to 0 in the next step. It gives me a trinomial on the left-hand side, and I factored it to get x plus 2 times x minus 6 equals 0. And the two values of x that make that equation true are negative 2 and positive 6. So there are two answers when you encounter a quadratic in these kinds of questions, and it's factorable in this way. In question C, I've given us a quick note here. I'm saying algebra is required, and specifically we need to divide both sides of this equation by the number 2. So this coefficient of 2 was presenting a problem initially. I want to have just the power term on that left side. And because it's understood multiplication between the 2 and the power term, I divide in order to get rid of the 2, and whatever I do to the left side, I do to the right-hand side. So 18 divided by 2 gives me the 9 here. I still don't have a single power term on each side with the same base, so I need to change the number 9 and express it as a power with a base of 3. 9 is 3 squared. And as soon as I have one single power term on each side with the same base, I can now shift to working with just the exponents. I write my therefore symbol down. Y minus 2 equals 2, and a little bit of algebra gets me to y equals 4. Again, if you wish, you should pause this video and just do a quick check for yourself mentally that when you sub in a y value of 4 into the left side, it gives you the same value as on the right side. And I encourage you to do that with any of these questions. Now in both questions A and C, I had a number that needed to be changed into power form. But coming up with the base for that number was not difficult because the base was evident looking at the other side of the equation. I had 3 to the power of x here, so I needed to express this with the same base number. In questions D and E, the base that we need to work with isn't evident in the original question, so you have to think a little bit more about it. We've got a base number of 32 and a base number of 16. Those are even numbers, and the ideal base to work with is the even number 2. Typically, we're going to be working with base numbers of 2 or 3 or 5. Most of the time, we can express the answers using those bases. The number 32 is equal to 2 to the power of 5. So I've merely changed the 32 into power form. The x plus 3 that was the original exponent is still here. Similarly, on the right-hand side, 16 becomes 2 to the power of 4. The negative 3x that was in the exponent position is still here. In the next step, I need to simplify the exponents. That involves using distributive property on the left. 5 times x is 5x, 5 times 3 is 15. And on the right side, 4 times negative 3x is negative 12x. So we're using the power of a power law that we worked with earlier in our lessons. I now have the same base number of 2 on each side and the simplified power term on each side. I know the exponents are equivalent to each other, so I write my therefore symbol, and I set those exponents equal to each other, and algebraically it works out to an x value of negative 15 over 17. In question E, I also needed to change the base numbers. I didn't do that immediately, however, because I have a more complicated looking expression on the right. We want to shift that so that it's up in the numerator position, and that's simply a matter of taking that original denominator, writing it in the numerator position, and then applying the exponent negative 1. And so I'm using the negative exponent law for this. I used distributive property next with that negative 1. I multiplied it by the x and the negative 1 inside the brackets in the exponent position. This is my new exponent. Now I'm ready to change the base numbers so that they match. 8 becomes 2/3, 16 becomes 2 to the power of 4. Simplify your exponents once again by using the power of a power law until you have a single base number, a single power on each side and in its most simplified form. Now the exponents are equal to one another, and a little bit of algebra gets us to the answer x equals 2 over 5. The last question in this section is a bit of a doozy, as I like to say, and I've given us some advice here. I've said we have a power term that's a common factor in this question. This is a very intimidating looking question to many a grade 11 student. They don't typically like them until they catch on to, oh, so that's how you do it. So I want you to focus on the left side and realize that there is a common factor of 10 to the power of n plus 3 that I'm going to take out of those two terms. Remember, when you're taking out a common factor, you're dividing the original terms by that common factor. So 10 to the power of n plus 4 divided by 10 to the power of n plus 3 is 10 to the power of 1. If that seems mysterious or uncomfortable to you, a quick check using distributive property shows that this is in agreement with that original term. So if I multiply this common factor by the number 10 to the power of 1, remember that means I'm adding the exponents together. And n plus 3 plus 1 agrees with the n plus 4 that I had originally. Similarly, this gets divided by, positive 10 to the power of n plus 3 gets divided by itself to give me the number 1. And again, a quick check multiplying this times 1 gives me that original second term in the equation. This is going to help me a lot, believe it or not, because 10 plus 1 works out to 11. And you might recall earlier, we had a question where we had to divide both sides by some number that was attached to the power term. Well, I have the number 11 that's multiplied with this power term. I want the power term by itself, so I divide both sides by 11. It gives me the power term by itself and the number 1 here. Again, this is often a place where a person might be stumped. They're thinking, I'm supposed to have the same base number. I just need to remind you that you can change the number 1 to 10 to the power of 0. And that way it has the same base as what you have on the left. And now the exponents are equal to each other. I write therefore n plus 3 equals 0, n equals negative 3. Sometimes a person doesn't readily see that 10 to the power of n plus 3 is the greatest common factor. Sometimes it's all they can manage to realize that 10 to the power of n is a common factor. So I'm showing another alternative to answering that very same question. That's why I'm saying versus this version of the question. So let's say we take out 10 to the power of n. Well, that means that I would have 10 to the power of 4. Again, keep in mind, multiplying powers are at the same base means add the exponents, so when I check, n plus 4 agrees with the n plus 4 that was there. And similarly, this term divided by 10 to the power of n is 10 cubed. Well, 10 to the power of 4 is 10,000. 10 to the power of 3 is 1,000. So it works out to 11,000 inside the brackets. I have to divide both sides by 11,000. I'm showing it here. But 11 divided by 11,000 simplifies to 1 over 1,000. And again, I want to express that as a power with a base of 10. So 1/1000th is 10 to the power of negative 3. And at this point, I have a single power term on each side with the same base, and the exponents are equal to one another. So n equals negative 3. This is one of those rare cases where we're less stringent about demanding that you take out the greatest common factor. In the end, we want to end up with the correct solution of n equals negative 3, and either way would be fine. They would be acceptable ways of getting there. The rest of this lesson focuses on applications of exponential equations. And in the first example, which I've dubbed party time, I've said, imagine that you, eventually, when it's safe, plan to have a party. And you send a message to your 3 best friends to invite them to the party. Here's you on day 0. You were the one sending that message. And on day 1, there's your 3 best friends who end up getting the message. Every day following that, each one of these friends passes the message on to 3 different friends, and so on and so on. So your 3 best friends are passing the message along. So by day 2, we have 9 people who are getting the message. Well, each one of those 9 people is going to pass that along to 3 other people. So we're going to have 27 people who get the message on the next day, which would be day 3. I have compiled this in a bit of a chart here. So day 0, there's your original message, your best friends on day 1. They passed it along to their friends. By the time we get to day 5, there's 243 messages that were sent. Kind of crazy, kind of impossible. I don't know. You might have heard stories of parties that have gone wild. At any rate, also in this chart, I have expressed these numbers, 1, 3, 9, 27, 81, in power form. Well, I've said here that the number is tripling each time, so our growth factor is 3. And this is the base number for the power term. So we have the base of 3 here. The number of days that have gone by or elapsed is the exponent in this case. So day 0 is there, all the way down to day 5. Notice it's the exponent on the base of 3. And our starting or initial amount is 1 message, so that's the coefficient. Normally I wouldn't write it there, but I'm trying to emphasize your starting amount always goes in that coefficient position. So the general equation that models this relationship is y equals 1 times 3 to the power of x, where x is the time in days, 3 is the growth factor, 1 is the initial amount, your one message that you sent, and the y is equivalent to the number of messages that have been sent at any time x. Note that these power terms are in agreement with the standard form of writing them. 3 cubed is 27. 27 times 1 is 27. It's kind of cool how that works out. The general exponential equation is y equals a times b to the power of x, where a is always your starting or initial amount, b is always your growth factor, if an amount is increasing, as it is in this case, and x is the elapsed time typically. Let's look at another example. It also involves growth. In this case, it's about wage increases. It said, suppose you start a job that pays $14 an hour. Every year you are entitled to a 2% raise from your previous year's hourly wage. I've said here, what number would you multiply $14 by to obtain the new hourly wage in 1 year's time? Well, if it's going up by 2%, and that gets converted to a decimal number, that would be 0.02, but that's on top of the 100% or the original $14 that you were making. So our growth factor in this case is 1.02. Again, the 1 is representing the original 14 bucks, and the 0.02 is the 2% growth. For example, after year 1, multiplying by that base number, a person would be earning $14.28 an hour instead of $14 an hour. Now, in the subsequent year, the person would be earning 2% of that new amount. So it's compounding. The amount of the increase becomes more dramatic as time goes on. It said here, write the general equation that models this relationship and use it to determine your hourly wage after being employed for 15 years. Well, I've started with the general formula for exponential functions. I've subbed in my initial amount, which is the $14. Here's my base, and x is present in the equation as well. So there's the general equation for this situation. And now subbing in an x value of 15 gives a new hourly wage of $18.84 after working for 15 years. Both of the previous examples involved growth, and when there is growth, the base number in the formula is always going to be a number bigger than 1. The base number was 3 in the first example. The base number was 1.02 in the second example. What happens when something is going down or decreasing in value exponentially over time? Well, example 3 deals with that kind of situation. It involves car depreciation, which means the decline in monetary value over time for a vehicle. So in this scenario, we're working with a car that has an initial value of $42,000, and it depreciates in value by 20% per year. Incidentally, most vehicles tend to depreciate between 15 to 20% each year that a person owns it. I've said since this value is decreasing by 20% per year, what I'm really interested in is how much is it worth after each year? Well, the remaining value at the end of the first year is going to be 80%. So if it's lost 20% of its value, it still has 80% of the original value. That's going to be the number that we focus on. We convert that percentage to a decimal number when we work with it in the equation. To find the value of the car, we need to multiply the previous year's value by 0.8 then. So when you're dealing with exponential growth, the base number is going to be bigger than 1. When you're dealing with decay or something that's going down in value, the number is smaller than 1. We call this the decay factor instead of the growth factor. Question 2 related to this says, write the general equation that models this situation and use it to determine the value of the car after 5 years. Here's my general formula. Here's the more specific formula based on the information from the question. My initial value is $42,000. My base is 0.8, and x is going to be the number of years that have elapsed. Well, after 5 years, subbing in that x value of 5, the car is worth $13,762.56. I purposely chose some simple numbers in the first example so that you could process this pretty easily in your brains. So if something loses 20% of its value, 100% minus 20% leaves you with 80% of the original value. Well, the numbers that we're working with in the next example are slightly less friendly, but we're applying the same idea. So the population of a city is decreasing exponentially by 1.5% each year. So if it's decreasing by 1.5% each year, 100% minus 1.5% is 98.5%. So at the end of each year, it still has 98.5% of its original population. In the year 2010, the population was 950,000 people. We're asked to write an equation that models the decline in population and use it to determine the population size in the year 2030. So I could have used y equals a times b to the power of x. I purposely changed it up a bit because you'll see this in textbooks as well. Sometimes we change the variables based on the context. So we're dealing with the size of a population, so I've used capital P for population and N for the number of years that have elapsed. The more specific equation based on this context involves a starting value of 950,000 people, my base number, remember 98.5% as a decimal is 0.985, and I've got that raised to the exponent n, which becomes a 20. The 950,000 people, that was in the year 2010. We're being asked to figure out what the value is 20 years later than that. So my exponent is 20, and because this equation was given in function notation style, I don't have to write sub n equals 20. That's already conveyed when I write p of 20. It works out to approximately 702,179.6. I need you to bear in mind that our units are people, living organisms, human beings. And you'll note that I tend to round down in these situations. This really is meant to be an estimate. If you round it up, that would be fine. We're just trying to get a reasonable ballpark idea, easy for me to say, of how big the population is. Again, I don't like envisioning 0.6 of a human being, so I tend to round down. Before I leave this section behind, I just want to point out or emphasize that for exponential growth, your growth factor is always going to be a number bigger than 1. Again, we worked with a growth factor of 3 in the party example and a growth factor of 1.02 in the wages example. For exponential decay, we call it the decay factor, and that's always going to be a value between 0 and 1. So 0 is less than b, which is less than 1. The b value cannot be 0. So if I have a b value of 0, I don't actually have an exponential relationship anymore. I've asked you to consider about this example here. So if I have a starting amount of 3, but my base is 0, it doesn't matter what exponent that's raised to. 0 to any exponent is still 0. 3 times 0 is 0. So the simplified equation is actually y equals 0. Not an exponential equation at all. In fact, that's an equation of a horizontal line. So in exponential equations, your growth factor is going to be a number bigger than 1, or your decay factor is going to be between 0 and positive 1. For most application questions, you can use the equation y equals a times b to the power of x. Or if you're dealing with a question that involves population, you might see a bit of variation in how the variables are expressed. So p of n equals a times b to the power of n, like in the previous example. There is a very special application of exponential growth involving money, and it's the compound interest equation that we're working with here. I've identified what each of the variables means to the side here. P is standing in place of the principal amount that is invested. That's an amount of money that a person is investing. A is representing the final amount after having invested that money for some period of time. The exponent n is the number of times that interest is calculated over the lifespan of the investment, if you will. The number of times the interest calculation is done over the specified period of time. And I is the interest rate per compounding period. It's important to note, you might not be super familiar with some of the notation here or the way that questions are worded. These are the options for compounding periods. If it's annually, it means once per year, obviously. Semi-annually, twice a year. Quarterly, 4 times a year, because there's 4 quarters in a year. Monthly, 12 times a year. Weekly, 52 times a year. And daily would be 365 times a year. This might make more sense once we get into an example. I've given us 4 different possibilities here with the same numbers. I've said, suppose that a Canada savings bond, which is a kind of investment, suppose that it pays 4.5% interest per year. You will often see that written in textbook questions, / and then an A. That A stands for the Latin word annum. And annum literally means year in English. So annum in Latin is year in English. Let's back it up. So we've got this kind of investment that is paying 4.5% interest per year. Our job is to figure out how much that bond or that investment would be worth in 5 years. So we're keeping the length of time the same. If the interest is compounded, and there are 4 possibilities. If the interest is compounded annually, then this is the simplest scenario of all. Remember, P is the principal of the amount invested, which is $5,000. I don't think I specified that there. I intended to. So we're investing $5,000 in every case. So P is 5,000. The 4.5% interest rate changes to 0.045, but the set of brackets has 1 plus I in it, so I put a 1 in front of that. And the specified length of time is 5 years. So that's my exponent. And I punch that into my calculator. It comes out to approximately $6,230.91. It's pretty good. You start with $5,000. After 5 years, you end up with $6,230.91. In B, the interest is being compounded quarterly. That means they're doing the interest calculation 4 times over the span of 1 year. in contrast to the previous example where they only did the interest calculation once and it was at the end of each year. So once per year for 5 years gave me an exponent of 5. 4 times a year for 5 years gives me an exponent of 20. And I show that off to the side. Again, my principle is the same. And we also have to be careful about the I value. So if interest is calculated more frequently than once a year, it's always going to affect your N value and always going to affect your I value. So I've taken that annual amount of interest, the 4.5%, changed it to a decimal number, but I have to divide it by 4. Because that 4.5% is over the span of the whole year. And when they do the interest calculation after the first quarter, they're going to be using this. So in each quarter, they earn this amount of interest, and 4 of these adds up to the original 4.5%. So you take your annual rate and divide by 4 when interest is calculated quarterly. That goes after the 1 inside the brackets. It came out to approximately $6,253.75. That's higher than what I had previously. It's roughly almost $23 more. So the more frequently the interest is calculated, the more it is to a person's advantage. They tend to earn more interest. And that's because they're calculating it every 3 months instead of just once a year. In the monthly scenario, still $5,000. Look at my exponent. It's a 60 this time. It's because they're doing the interest calculation 12 times every year for 5 years, which works out to 60 times altogether. The 4.5% interest rate gets divided by 12. So we're trying to figure out how much of the interest rate do they get each month. It works out to this decimal value, which I tagged on after the 1. Putting that into my calculator gave me a slightly higher amount than what I had earned, or it would have earned in Part B. Again, the more frequently that the interest is calculated, the higher the total amount will be at the end of the period of time. When interest is calculated annually, you just use the interest rate that you see in the question in the brackets following the 1. When interest is calculated quarterly, you have to divide it by 4. When interest is calculated monthly, you have to divide it by 12. And if interest is calculated daily, it has to be divided by 365. And the exponent in this case is 5 years times 365 days per year. It works out to 1,825. So there's my N value. P value is the same. When I did this division on my calculator, it gave me a very long decimal number, and rather than write a very long decimal number, I also want you to get comfortable with having a fraction there. Sometimes you won't get a terminating decimal when you do this division and you're coming up with your I value. Well, it's not acceptable to just cut off some digits of accuracy. We want to end up with the most accurate answer we possibly can. So there will be times where you just have no choice. This will not divide and provide a terminating or ending decimal, and you'll have to use the fraction. So you need to get comfortable with punching that into your calculator. If you do that successfully, you should get approximately $6,261.53 for the result. You might want to just put $5,000 here in the question before we leave this behind so that it's clear that I really did intend to give you the principal amount in this question. Thanks for staying with me so far. We just have one more question to do, and it's a bit of a twist on what we were just looking at. In this question, we're being asked to figure out the principal amount. We're being given a known amount that we want to have after a period of time. It says how much money must be invested now. So we don't know the amount to invest now. That's the p-value. At 3% per annum, or per year, compounded quarterly, in order to be worth, for it to be worth $12,000 in 10 years' time. Well, I've organized my thoughts off to the side here. I know that the amount we're aiming for is 12,000. The n value will be the number of years times how many times they do the interest calculation per year, which is 4 times a year. So n is 40. My value of I is the annual interest rate divided by the number of times they do the interest calculation each year, which is 4. And it works out to a convenient decimal number. It's the principal that I don't know. Here is the compound interest formula. I merely just rotated it around, and I did that for convenience sake because I want to isolate p. So I wanted to have it on the left-hand side. I divided both sides of this original formula by that expression in the brackets. 1 plus I to the power of n goes into the denominator on the other side. And now I'm ready to substitute in the values. My a value is 12,000. 1 plus the I value is there, and my exponent is 40. Again, you'll want to make sure you can punch these into your calculator and get the answer accurately. This works out to approximately $8,899.78. So that's the amount that would have to be invested now in order for it to grow to $12,000 in value 10 years later. And that's the end of the lesson. I wish you well. See you next time.